So in this video, we're going to be looking at solving logarithmic equations and exponential equations. We'll use properties that we were just talking about, properties of logarithms. So first of all, again, you need to remember what it means. The logarithmic function, to have base a, your base has to be bigger than 0, and your base cannot equal 1. Then y equals log base a of x, which just reads y is the logarithm to the base a of x, is defined by, so y equals log base a of x. This is if and only if x is equal to a raised to the y power. So recall, when we're looking at logarithms, we need to make sure that that argument that we're taking the logarithm of is bigger than 0. So we had just went through all of these properties. So basically, if you have base a and that's raised to the log, same base as the base of our exponential a of m, that's just going to be the argument of that log m. Log base a of a raised to the r power, that was equal to r, just the exponent. Log base a of m times n, multiplication in between our logarithm, we can rewrite multiplication in between the argument of the logarithm, we can rewrite as log base a of m plus log base a of n. If you had log base a of m divided by n, we can rewrite that as a difference of two logs, log base a of m, the numerator, minus log base a of n, the denominator. If you have an exponent on your log, so log base a of m, the argument is raised to the r power, we can bring that exponent down from the logarithm, and that's the same thing as r times log base a of m. A to the x, that's the same thing as e to the x times the natural log of a. And what we just saw in the last video, if m is equal to n, then log base a of m has to be equal to log base a of n, or the opposite direction. If you have log base a of m equals log base a of n, then m must equal n. Okay, so we're going to use these properties to help us solve logarithmic equations and exponential equations. So we have some strategies when we're going about solving logarithmic equations. So you want to start the following. So rewrite your equation using properties of logarithms so that it is written in one of the following two ways. So if we can get it where we have a single log equals a constant, so log base a of x equals c, or we can write it as log base a of something equals log base a of something else, then we could use that property where we could just drop our logs and set our arguments equal to each other. If we can't manipulate it to be a single log equal to a single log, then this is where you would want to do the following. So if the equation is in the form of log base a of x equals c, so we can manipulate that to look, our equation to look like that, then change it to an exponential form, undo the logarithm, and solve for x. If the equation is in the form of log base a of something equals log base a of something, use that property a to get rid of the logarithm solve. I didn't state any properties, I guess, up here. I said it's a, which I just stated. And for logarithms, we need to be careful. We need to check. We might get what are called extraneous solutions. And we saw that before when we were solving rational equations, or we were raising both sides of our equations by an even power. So this is another case where you might get extraneous solutions. So you need to check your solutions. Remember that the domain of a logarithmic function, y equals log base a of x, that argument x has to be greater than 0. So the first example in front of us, we have log base 3 of 16 equals 2 log base 3 of x. So I have log equal to a log. I just can't drop that log right now because of this 2 in front. And so we can use properties of logs and we can rewrite this. So this is the same thing as log base 3 of 16 equals that coefficient in front can be rewritten as log base 3 of x, and that coefficient is making us square our argument, so x squared. So if we have a log same base equal to a log same base, and then we can say, well, then our argument here, 16, must equal x squared. So solving this, I could either subtract 16 and factor, or I can use the square root method, taking the square root of both sides. So I would get plus or minus the square root of 16 equals the square root of x squared. Square root of x squared is x is equal to plus or minus the square root of 16 is 4. Problem is I can't have a log of a negative number. And if I plugged in negative x in here for x, I'm sorry, not negative x. If I plug in negative 4 in there for x, then I would have a log of a negative number. So x cannot be negative 4. And so we only get x equals 4 as our solution. So the next example in front of us, we have log base 2 of parentheses x plus 2 and parentheses plus log base 2 parentheses 1 minus x, and your parentheses, this is equal to 1. Okay, so I notice I cannot manipulate this to be a log equal to a log because of that 1 there. And so I want to rewrite this as a single log. So addition in between my logarithms, I can rewrite as multiplication. So I have log base 2 of this x plus 2 all times this 1 minus x. And this is equal to 1. So we can either distribute now that x plus 2 all times that 1 minus x, or we can distribute later. I noticed that we're going to need to distribute either way. And so we might as well just distribute now, or at least partly. So we have x times 1 is x. We have x times negative x, so minus x squared. We have 2 times 1, so plus 2. And then we have 2 times negative x, which is negative 2x. This is all times, or all equal to 1. So let's use our rules or our definition of logarithms to rewrite this as an exponential equation. So our base of our log is the base of our exponential. This other side of our log is our exponent of our base. So we have 2 raised to the first power. This is equal to our argument, which is, I'm going to rewrite it in descending order of powers here, and I'm going to combine at the same time x minus 2x. So I have equals negative x squared. So x minus 2x is minus x, and then plus 2. So I notice here I have a quadratic equation, and I know to solve for quadratic equations, I like to set my equation equal to 0. I also like my coefficient in front of x squared to be positive 1. So let's add x squared to both sides of the equation, and we would get x squared. Let's add x to both sides of the equation, so plus x. And then let's subtract 2 on both sides of our equation. And that 2 to the first power is 2, minus 2 gives us 0. And this is equal to, we got everything up to the other side, so this is equal to 0. So let's factor it. They both have an x in common. So pulling out an x, we have x times the quantity x plus 1. This is equal to 0. So at each factor equal to 0, we have x is 0 or x plus 1 is 0. So we have x is 0 or x is negative 1. We need to check. We can't have a log of a negative number. So if we went back in and we plugged in 0, wherever we saw an x up here in our original equation, that would be 0 plus 2 for the first argument, which is positive. It's 2, so that's okay. And for the second argument, for that second log, 1 minus 0 is 1, so that's okay. So we're okay with x equals 0. Now let's look at x equals negative 1. So if we go back in here to our original equation, I would have negative x plus 1 as my argument, which is positive 1. So it's positive. I'm okay. And then I would have, for my second log, I would have 1 minus a negative 1, which is really 1 plus 1. So that's also positive. So these both give me logs of positive numbers. And so we can use both of those as our solution. So both give us a log of a positive number. So we are okay. We don't need to exclude any of those solutions or answers from our solution set. So the next example, we have the natural log of the argument, which is x minus 1. And then we have plus the natural log of x. And that is all equal to the natural log of our argument x plus 2. I noticed that I could rewrite the left-hand side of my equation. I have addition in between my two logs. So I could rewrite that as a single log, the natural log of my argument x minus 1 times the argument x plus, or no, just x. And this is equal to the natural log of x plus 2. So I have a log equal a log. We have the same base, which is an e. So we can technically just drop our logs and we can say, well, our arguments are equal to each other. This x minus 1 all times x must equal x plus 2. So let's solve this. Let's expand. Let's distribute our x to the x minus 1. So doing so, x times x is x squared. And negative 1 times x is minus x. So this is equal to x plus 2. Quadratic, so let's set it equal to 0. So let's subtract this x on both sides of our equation. And let's subtract 2 on both sides of our equation. Doing so, we would get x squared. So negative x minus x is negative 2x. Minus 2 is equal to 0. Unfortunately, it doesn't look like we can factor that. There's no two numbers I can multiply to give me negative 2 and add to give me negative 2. So it looks like I'm going to need to use either the quadratic formula or I can complete the square. So I would jump in and use the quadratic formula. So we have here x is equal to negative b, so 2 plus or minus the square root of negative b squared. I'm sorry, not negative b squared. So negative 2 quantity squared is 4, minus 4 times a, which is 1, times c, which is negative 2. So negative 4 times negative 2, so plus 8, all over 2 times a. So 2 times 1 is 2. You get x is equal to 2 plus or minus the square root of 4 plus 8 is 12, all over 2. I notice that I can break down that square root of 12 and pull out a factor that is a perfect square. So this is 2 plus or minus the square root. Well, 12 can be rewritten as 4 times 3, all over 2. So this is the same thing as 2 plus or minus square root of 4 is 2. So put the 2 outside of the square root, and then times the square root of 3 all over 2. So we can either think of this as factoring out a 2 from both of these terms in the numerator and then canceling what is in common, or we can think of it as rewriting that as 2 separate fractions. If I factor out a 2, we have 2 all times the quantity, 1 plus or minus root 3 all over 2. So we can simplify by canceling out our 2's. And so we get 1 plus or minus root 3. So again, I need to check to make sure that I don't have a log of a negative number. So I'm estimating that square root of 3. Well, that's between square root of 1 and square root of 4. Square root of 1 is 1, square root of 4 is 2. So that square root of 3 is between 1 and 2, 1 point something. So if I have 1 minus a root 3, that's going to be a negative number. A negative number up here, a negative number minus 1 is negative. So I know x equals 1 minus root 3. That's going to give me a log of a negative number. So this one, it can't work. So let's look at x equals 1 plus root 3. Well, because square root of 3 is 1 point something plus that 1 in front, so that's 2 plus something. So plugging in 2 plus something in here, 2 plus something minus 1 is positive, so I'm okay for the first natural log. 2 plus, or 2 point something, that's positive, so we're okay for the second natural log. And on the other side, 2 point something plus 2, that's positive, so we're okay. So our solution here is only one of the ones that we got, which is x is equal to 1 plus square root of 3. So the next logarithmic equation we have is log base 4 of x plus 3 minus log base 4 of 2 minus x equals 1. So let's rewrite this as a single log. We have minus in between our logs. So that would be log base 4 of our x plus 3. Minus is division, so divided by 2 minus x. This is equal to 1. So I don't have a log equal log, but I have a single log equal constant. And so I could rewrite this in exponential form. So I have my base is 4. So we have 4 raised to the other side, which is 1, is equal to my argument, this x plus 3 divided by 2 minus x. So we've dealt with solving for irrational equations before. So we want to get rid of our denominator. So let's multiply both sides of our equation by 2 minus x. So distributing our 4. Now 4 times 2 is 8. Minus 4 times x, so 4x is equal to our 2 minus x's cancel, and this is equal to x plus 3. So looking at this, this is a linear equation, so I know I want the terms with x on one side and the terms without x to the other side of the equation. So let's, how about add 4x to both sides? And let's subtract 3 on both sides. So doing so, 8 minus 3 gives us 5 on the left-hand side of the equation is equal to x plus 4x, which is 5x. Let's divide through by 5 to get x by itself. So we get here x is equal to 5 divided by 5, which is 1. So again, I need to check, make sure I don't have a log of a negative number. So if we go in and plug in 1 wherever we see an x in our original equation. So 1 plus 3 for that argument is 4. So I'm okay. That's a log of a positive number. And over here I have 2 minus 1. And 2 minus 1 is 1. And that is also a positive number. So I don't have any extraneous solutions there, and I have the solution x equals 1. So the next examples that we're going to look at are solving exponential equations. Looking at this first one, I have 9 raised to the x power minus 3 raised to the x power minus 12 is equal to 0. So notice this. I notice 9 is the same thing as 3 squared. Okay, so let's rewrite this 9 raised to the x power. This is 3 squared raised to the x power minus 3x, or 3 raised to the x power, minus 12 equals 0. So recall power to power, we multiply our exponents. So this is 3 raised to the 2x minus 3 raised to the x minus 12 equals 0. I notice I can manipulate this to look like a quadratic equation, and then we could do substitution, which we had looked at doing stuff like that at the beginning of the semester. So notice that this is the same thing as 3 raised to the x. Let's put the square out here. Quantity squared minus 3 raised to the x minus 12 equals 0. So let's choose maybe u. Let u equal this 3 raised to the x power. So if we go back in and we substitute in u, wherever we see 3 raised to the x power, we have u squared minus u minus 12 equals 0. So I notice this is factorable. There are 2 numbers that multiply to give me a negative 12 and add to give me a negative 1. So I can factor this as u minus 4 all times u plus 3. So u minus 4 is 0 when u is 4, and u plus 3 is 0 when u is negative 3. The problem is I want to know what x is, not what u is. And so let's maybe do it up here. We have 2 separate equations. We have 4 is equal to 3 raised to the x, and we have negative 3 is equal to 3 raised to the x. So the trick, we were solving exponential equations before, but we were always able to manipulate those bases to be the same. So here in this section, we're not necessarily going to be able to manipulate the bases to be the same. And so we want to use properties of logs. We know a log of something raised to a power, we can bring that power down front. So we want to take the log of both sides of this equation. I usually either take log base 10 of both sides, or I take the natural log base e of both sides. Either way, you're going to get the same answer. And so let's take the natural log of both sides. So this is the natural log of 4 is equal to the natural log of 3 raised to the x power. So now I'm going to use that property of logarithms where I can bring my exponent down in front of the log. So this is the natural log of 4 is equal to x times the natural log of 3. So I want to get x by itself. I notice I could divide both sides by the natural log of 3. So I get x here is equal to the natural log of 4 divided by the natural log of 3. I cannot cancel those natural logs out. Those are functions. And so I get, for the first equation, x is equal to the natural log of 4 all over the natural log of 3. The second equation, I notice that that's impossible. There's no way that I can raise 3 to some power to get back negative 3. But if I didn't see that, I would either try to manipulate the bases to be the same, or I would take the natural log on both sides of that equation. And so if we took the natural log on both sides of that equation, I would get the natural log of -3 equals the natural log of 3 raised to the x power. But we have a problem because we can't take logs of a negative number. So this is undefined. So there's no solution to that equation. And so we have one solution, and that is the natural log of 4 all divided by the natural log of 3 is what x is. And notice that my next example there is what we just solved for when we were solving for the equation above. So we have 3 raised to the x power equals 4. So just take the natural log of both sides, bring down your exponent, and then divide by that natural log to get that exponent x by itself. So I have another example in front of us. We have 2 raised to the x minus 1 power equals 5 raised to the 2x plus 3 power. Notice base 2 and base 5 can't be manipulated to be the same. And so we're going to want to take the log of both sides of our equation. So we can do log base 10 on both sides, or we can do natural log base e on both sides. So taking the natural log of both sides of our equation, we have the natural log of 2 raised to the x minus 1 power is equal to the natural log of 5 all raised to the 2x plus 3 power. So we're using properties of logs to bring our exponents down in front of our natural log. Notice they'll have more than one term in that exponent. So we need parentheses around that whole exponent, or what you're writing is not mathematically correct. So we have that quantity x minus 1 in parentheses times the natural log of 2 is equal to parentheses 2x plus 3 and our parentheses all times the natural log of 5. So the natural log of 2 and the natural log of 5, those are just coefficients. They're just some number. And so let's multiply. Let's distribute our natural logs inside the parentheses. So doing so, I would have x times the natural log of 2. I'm going to keep the x out front just so that there's no confusion that that x is not part of that log. And then minus 1 times the natural log of 2. So minus natural log of 2 is equal to 2 times x times the natural log of 5. So 2 times x times the natural log of 5 plus 3 times the natural log of 5. So I have 2 terms in here that have an x in it, and I want to get x by itself. So the trick is to get all the terms with x on one side of our equal sign and all the terms that don't have an x on the opposite side of our equal sign. So let's subtract. So we have x natural log of 2. Let's subtract 2x natural log of 5 on both sides. So minus 2x natural log of 5. This is equal to 3 natural log of 5. And then let's move this minus natural log of 2 over to the other side by summing it to both sides. So this will be plus natural log of 2. So we can factor out an x here from both of those terms. If we pull out an x from both of those terms, we're left with the x times the quantity of the natural log of 2 minus 2 natural log of 5 is equal to 3 natural log of 5 plus natural log of 2. So if we divide both sides by that parentheses that is multiplied to the x, then we get our x by itself. So we have x is equal to, our numerator is 3 natural log of 5 plus natural log of 2. This is all divided by natural log of 2 minus 2 natural log of 5. So on an exam, I'm going to want you to be able to solve a lot of these without a calculator. So I might just say, leave this as an exact form. Same thing on your homework program. It might ask you a couple of different things. It might say, give me the exact answer, which would be this. And then it might ask you to round your answer. So plug that into the calculator and simplify. If you were to plug this in the calculator, make sure that you have parentheses around the whole numerator, divided by parentheses around that whole denominator. And make sure that when you're plugging in your argument to your natural log that you're closing off those parentheses.